solution, okay, or optimal solution. But in fact, what they do is that they give you the correct or optimal solution with a certain probability. Okay, so that's the basic idea. And of course, if you have a probabilistic algorithm, then to get to the correct solution, what you want is you can run the algorithm many times, and as you run it again and again, then the probability will become arbitrarily close to 1. Okay, so we are going to start by talking about something called Bloom filters. It's a nice transition from hashing because it's really another application of hashing. Okay, so you have, let's say, you have a hash table, and the keys that you want to store in the hash table are very large. Okay, so then what happens is that the amount of storage you need to have is m times w, where m is the number of entries that that you're putting into the hash table, and w is the number of bits you need to store each key, right? So if you are each element, okay, so if the elements are very large, then the amount of space you need can become very large. So what if, right? So if you want to store very large keys, then the hash table size can become large. Okay. So the radical idea is you say, okay, W is large. Okay, I won't store W. Right? I just will not store the keys. I will just have some fancy way of figuring out whether something is in the hash table or not, but I won't necessarily store the value. Okay. So if I could do that, then of course I have a W-fold reduction in space. So once again, if I'm talking about very large data structures, this is going to be a significant reduction. Okay. So the way Bloom filters work is that you exactly do that. All you're going to do is you're going to hash, and then the hash is going to result in a number, and you maybe your hash table itself is simply a bit vector, and you hash your key into your value, and you go to that bit and you set it. Okay. Except that if you just set just one bit, then it's quite easy to run into collisions. So the basic idea, the difference in Bloom filters is that you're going to use multiple hash functions. And the idea is that, well, if you have multiple hash functions, then two keys that collide on one hash function will not necessarily collide on the other. And so if you have k hash functions, then you hopefully achieve some sort of an exponential reduction in collision probability. Okay, so let's say you use k hash functions. And the hash table, as I said, is simply a bit vector. Okay, so let's look at how this picture helps, right? So this is your hash table, a bit vector. Okay, and what you're going to do is to insert a key. What you're going to do is you're going to take that key and then hash it using the k hash functions. In the example, we have k equal to 3, right? Yes, k equal to 3. So what we do is we compute h1 of x. Okay, h1 of x happens to be 1, and so we go to the first element, right? Not the 0th element, but the first element, and we set it to 1. Again, x is that h2 of x happens to be 5, right? h2 of x happens to be 5, and once again you go and set the fifth bit to be 1, and h3 of x happens to be something too large for me to count, but again you can see, and that bit is set to 1. So inserting a key into your Bloom filter means you basically compute the k hash functions on the value, right? And then you go to those bits and set them all 1. Okay? And you can see that here is 3 elements that are inserted, x, y, and z. And you can see that some of them, like x and z, on the second hash function, x and z have the same value, right? They produce the same value. They collide on the second hash function, right? X and z collide on the second hash function. So whenever this bit is 1, right, that alone you cannot figure out whether it is an x or a z, right? But what you do when you look up is that, once again, you're going to follow the same process. You're going to apply H1 through Hk, and then you're going to go and check all of those bits. And if all of them are set, then you can say that that particular element is in the hash table, right? If not all of them are set, then you can say even if one of them is not set, then you know for sure that it is not in the hash table, right? Yeah?
Is it the possibility like each of the hash functions give the same index for a particular?
Yes, of course, and it is once again, right, I mean, you can just argue on the basis that U is so much larger than N that there must be elements where, you know, these sorts of things tend to happen, okay? So, yes, the point is that you cannot avoid collisions, right? All you can do is you can reduce the probability of collisions by using multiple hash functions, but you cannot eliminate them completely, okay? And as a result, what happens with this is that you can have false positives, right? Just because a bit is set doesn't necessarily tell you it was that particular element that was set. So for instance, in this case, right, you can see that W shares, you know, two of the hash functions produce, you know, lead you to cells that are already 1, okay? Even though W itself is not in the hash table, right? So you haven't really inserted W, you are looking up whether W is in the hash table, okay? And you apply the hash function H1, well, that bit is set. You apply the hash function 2, that bit is set. And then you apply hash function 3, turns out that that bit is 0, then you can immediately tell, okay, it's not there, right? Because if W was there, then every one of those bits you would have set, right? So even if any one of them is not set, then you know for sure that that particular element is not there. But again, it's possible that there was another U that was inserted into the table, and that U, you know, that insertion of that U caused that 0 also to become 1, in which case you will look up for W, even though W was never inserted into the table, you might, your check tells you, okay, it's there. And so this is the notion of a false positive, right? So you can have false positives, and then you can only talk about, okay, you know, what is the probability? But there cannot be a false negative, right? So once you put something into the table, if you go look it up, it's going to be there, because there is no operation that takes a 1 and turns it into a 0. Okay? You can only turn it from 0 to 1. And why is there no such operation? Because we cannot do deletions in this data structure, right? Suppose we add x and then y, right, and z, and then we go back and try to delete x. We cannot possibly set this to 0, right? Because we don't know whether that 1 came from x or it is set because of some other value, right? So if we just go ahead and eagerly set that back to 0, then we might end up deleting not just x, but other elements, right? So as a result, with this data structure, you have to give up on being able to delete data items, okay? And yes, there are actually some extensions to the Bloom filter data structure to allow you to delete, but these extensions, you know, tend to take away the good with the bad, right? So the Bloom filters have certain benefits. If you are willing to compromise some of those benefits, then you can have the ability to delete, okay? So for practical purposes, you can say Bloom filters are a type of data structure, a probabilistic data structure, right? With high probability, okay, will not have false positives, okay, and of course it will never have false negatives. Okay, so if you put something in there and you look it up, you can be sure that you'll be told it's there, right? But if you never put something in there and you look it up, you might occasionally be told that it is already there. Okay, so this false positive is definitely a possibility. Okay, so let's do our probabilistic analysis. Okay, the analysis, again, you will see that it is not particularly different from what we have seen before. At least it should sound quite familiar. Okay, so let's say we are asked to what is the probability that a certain bit is not set when you insert a key using one hash function? Well, of course, that one hash function could produce any of the m values, right? And therefore, the probability that any particular cell was not touched is 1 minus 1 by m, right? So basically, there's only 1 by m chance that this particular cell was picked by the hash function h1, right? And then, well, what happens if I complete the insertion of one key, which means that I'm going to apply h1 to hk. So I'm going to set k bits, right? So each of those k operations shouldn't have touched this particular bit. Well, we have this, again, the standard calculation, 1 minus 1 by m, because 1 minus 1 by m is the probability that it didn't hit this cell in one attempt. So if you make k attempts, then this is a probability that it didn't hit it in any of the k attempts. And again, we know that this particular, now if you're not inserting just one key, but let's say r keys, well then you just have kr attempts, right? And each of the kr attempts hasn't touched this cell, well then that probability is 1 minus 1 by m power kr. And we know that this 1 minus 1 by m power something has a relationship to E, and the particular relationship is this one, right? E to the power minus kr by m. Okay, you can work out why that is. It's not a. It's just some little bit of arithmetic. Okay. So the probability that a certain bit is set is, of course, you just complement it, right? So it's 1 minus e power minus kr by m, and then if you want to compute what is the false positive probability on a key y, well, the key y is going to examine k positions in the bit vector, and then all of those k positions must be set to 1, right? That's when you're going to have a false positive. And we already calculated that the probability that any one bit is set after r keys have been inserted into the table is 1 minus e to the power minus kr by m, correct? So after inserting r keys, this is the probability that any one bit that we take at random in the vector is going to be set. Now, if you want to have k such things set, well, once again, we just raise it to the exponent k, and because we don't like to keep saying e to the power minus kr by m, we'll just call it p. Okay. Now let's look at that number and see, what we can say. Okay, because not very easy to understand it right away. So let's just try to plug in some values and see, how it behaves. Okay. So if you let k to be 20, m to be 10 power 9 bits. Okay. Now 10 to the power 9 bits is approximately 12 megabytes. That's a billion bits, right? So the billion bits. Billion bits is, I guess it must be 120 megabytes, right? 125 megabytes. That's what it should be. I have a typo there. Okay, so. So the point is that if you crank the numbers, you will see that with a false positive rate of 10 to the power minus 3, you can store 60 million keys of arbitrary size. Right. The key point here is, again, notice that the key size doesn't matter. Right. You can store the key size is completely irrelevant. Right. And all that matters is how many keys you store, right? So that's why Bloom filters are useful when you need to store, very large state, very large entries or very large objects. Then you have a way of storing them without having to really store them. So, but the problem, of course, is that if k equal to 20, that means each insertion you have to compute 20 hash functions. Right? So this is not exactly very efficient. So there's a trade-off between how much you can pack into your Bloom filter and how long it takes, right? So by increasing k, that means you're going to check in k different places, which means, the probability of false matches is going to fall down, right? So by increasing k. But at the same time, when you increase k, you increase the overhead for inserting and looking up every one of those keys, right? So obviously that's a trade-off, and one has to choose the right point, okay? But let's say even if you're willing to pay a lot of time in order to save space, that still doesn't mean that you just keep making k excessively large, because there is a point at which it doesn't help, and you can at some point I'll give you an exercise to figure out this optimal value. So one of the things to remember is, okay, so there are situations where, two main situations where Bloom filters are very useful, right? So one of them is you are given a situation where you have a large number of keys to store. The keys are very large, and you simply do not have the memory to store them. Okay? If you don't have the memory, then you don't have the luxury of asking, do I want to tolerate false positives, right? So you just don't have the memory, so you have to, do with what you have, right? So that's one scenario where Bloom filters can be useful. The second scenario is that, let's say you have a real hash table where the keys are stored, but this hash table is offline, right? Maybe it's on the internet, maybe it's a distributed cache over the internet, or maybe it is in the disk, on the disk, and it will take a long, it'll be much more expensive to go to the table on the disk and ask it, does this element exist, right? So what you can do is you can say, okay, I can instead look up on the Bloom filter, and if the Bloom filter says the key doesn't exist, well, then you saved a lot of time, right? If it says it exists, well, then you might have to go to your slow backup and figure out whether it's actually there or it's a false positive, right? But if you think of it as a performance issue, then, well, if you have a false positive of 1%, that means, you will get a performance that is very close to the main memory performance, right? Versus, although from a correctness perspective, you lose nothing, but from a performance perspective, you get the performance of a main memory hash table, when in fact your data is so large it doesn't fit in the main memory. Right? So these are the two scenarios where Bloom filters are very useful. So any questions? Yeah.
Eventually when we have more deletions and insertions in the hash
No,
table.
remember there is no deletion.
Yeah, so means we are not deleting, but maybe means like the elements which we don't need in the main table. So we will keep in the hash table, but they will no more exist in the table. So we will have more cases of false positives eventually, because more of the bits will be 1.
Correct. But again, remember that time is, when we talk about these things, right? So it's easy to make time kind of irrelevant, because there's only so much time that can expire before your computer dies or the universe explodes or whatever, right? So what I'm trying to say is that these are the numbers we are dealing with here can be so small that the effect of time may not be a big issue. Anything else? Okay, so the second probabilistic algorithm we are going to talk about is one that